So the dot product is a multiplication of vectors. So given, let's say, vector A is x1, y1, and vector B, x2, y2. So two vectors, the dot product, or A dot B. And notice I might say A dotted with B, or the dot product of A and B, anything like that. So the dot product of A and B is x1, x2 plus y1, y2. Now looking at that, is this going to be a vector or scalar? It is a scalar, yes. So if we had, say, A is 1, 5, B is 2, 7, what is A dot B? Okay. Yeah, so we do 1 times 2 plus 5 times 7, which is 37. And we get 2 plus 35. Now, our dot product is going to be unique. Meaning, if I told you the dot product was 37, could you get me the two vectors? No. Could you get one of them? Okay? If I told you one of them, could you get the other? So let's say if I told you, notice if I gave you C equals 5, 9, and I told you C dot D equals 40. So could you tell me what vector D was? Okay? Could be or must be. Okay? So can you tell me what it must be? Okay, so your dot product is not a specific answer that will generate a single solution. Because we could look at this, and we could probably come up with several different answers that would generate this. So just having the dot product and one vector does not automatically tell you the other. Now you could come up with a vector, or several different vectors, and that's probably with an infinite number of vectors, given enough time. The question becomes, what is the dot product useful for, right? One of the things, A and B are orthogonal if and only if A dot B equals 0. What does orthogonal mean? Have you seen the term before? What? Okay. Orthogonal means they are at right angles. So these two vectors would be orthogonal. Possibly. Or to determine the orthogonality of them. Orthogonality would just be, are they orthogonal? Good. An interesting question. If I had A equals 5, 7, is it orthogonal with the 0 vector? Okay? Which is an interesting characteristic. Is the zero vector necessarily at a right angle compared to it? No, so this right angle idea is not entirely correct, but if it has magnitude. So let's look at a graph and come up with two vectors that are definitely orthogonal and test them. So what is a vector orthogonal to this? The negative 2, 3? Oh, negative 2, 4. Okay, so our two vectors, we had negative 2, 4, and 4, 2. So negative 2 times 4, negative 8. 4 times 2. So if they are orthogonal, you get the zero vector. Or it's not zero vector, it's the 0. What if I move this to the opposite side? Are these orthogonal? They had 2, negative 4. 2 times 4 is 8, plus negative 8 equals 0. So again, they are orthogonal. What? Yeah. You flip the other one going down there. So orthogonality, basically we're saying it is perpendicular, and except in the case of the zero vector. Now, some of the uses of this. One of them is the angle between two vectors. So given I've got a vector here and a vector here, what is the angle between them? Okay, how would you go about calculating this? If we knew this one was, I don't know, if we knew this location, we knew this one, say this was, I don't know, 2, 4, and this one was, say, 1, 8.
Do you find the right angle for the bottom one and the top one? And then do the vertical one and flat?
Are you talking about this?
No.
Okay.
Do you do it like find the right angle from the back?
So here, so are you talking about this?
Yeah.
Okay, how?
What you can.
What are we trying to do? Okay, determine how big this angle is. Could you get this angle right here? Let's just say that speed. Could you calculate speed? Should be easy. Okay, this is 1, this is 8, inverse tangent. Right? Could we calculate this one?
Really, I have to
No.
do this?
No, we could do this, right?
Yeah.
It would be relatively easy, but a fair amount of work. Thankfully, there's an easier way. So, I want to make sure you guys could see how we could do this manually before we got the formula.
Yeah.
So you can appreciate the formula a bit more. So our formula, dealing with this, so between two angles, cosine of theta is equal to A dot B, easy to get, right, if you know the two vectors,
Right.
divided by length of A times length of B. Magnitude, yes. So we're given, so we've got 1, 8, and 2, 4. So 1, 8, and 2, 4 for this one. So what's A dot B?
Isn't the triangle you do for 1, 8? That's an 8, 1.
8, 1, yeah. Okay. I'll switch it. Make you happy. 8, 1. Okay. So, what is A dot B? Okay, so 8 times 2 is 16 plus 4, 20 over length of A. Okay. A squared plus B squared equals C squared, so square root of 65. A squared plus B squared, so 2 squared 4 plus 16 square root of 20. Now, should we rationalize the new denominator?
Yeah.
I'll say no, don't do it. Because that's not our goal. What's our goal? Theta. Our goal is finding theta. It doesn't, we don't even need to deal with what that is. We're not stopping there. So how would you solve this then?
Inverse.
Yeah, cosine inverse of this, cosine inverse of that. So, let's see. The inverse cosine of, what was on top? 20 divided by, you parentheses, square root of 65 times square root of 20, was it? 20. Yeah, I'm in radian mode. So it doesn't matter which mode you're in, but it depends on what type of answer you want. So 56.3 degrees. I think it's a little easier that way than going through the basic math scale. What? Okay, you would set up this triangle, figure out B. Set up this triangle, figure out whatever I want to call this one, gamma, and subtract. Yeah. But no, this one you're just multiplying, adding, and then squaring in.
Wait, was that right triangle?
Well, we have to set up 2 right triangles, yes. One here and one here. The inverse, we could say the inverse tangent of this angle minus, or of this divided by this, minus the inverse tangent of this divided by that. So it's simple, it would work that way too. Except for, what if we start getting more complicated ones? Like say if you're doing here, and say something way over here. Then it gets even a bit trickier. Or maybe instead of there, and here. So the rule will still work. This rule. This rule will still work. It'll still say the answer. Whereas the other, doing the tangent method, it will be a bit trickier. Now the next part, projection. Now, easiest way to simulate a projection is something like this. I got a vector here on the ground, and I'm going to put another vector. When we look at this, say if we had a vector here and a vector here. We want to know how much of, say, this vector is in the same direction as that vector. So we have to be able to divide u into 2 parts. One part that's this way, and one part that's this way. Because this bottom part of, say, vector A is the projection.
We have to figure out how to like take the fire from somewhere.
Yes, except for instead of just being in x and y at any angle. That's what makes it more complicated. Thankfully, we've got a nice formula. How much of u goes in the same direction as v? Any vector we want can be divided into 1 or 2 or more vectors. U, for example, vector u could be the same as vector a plus vector b. What? Vector a plus vector b is u. Okay? And we want to know, how do we get vector a? Because a is going in the same direction as b. So the formula for projection of U onto V is this. And the notation we use. Projection of U onto V, V is a subscript here, is equal to U dot V divided by the magnitude of V squared times vector V. This part right here gives us the length of it. This is a U right here, this is a V.
Why is that notation on the right side of the equation?
Projection of U onto V. And it's cleaner when you use it in bold letters as opposed to the little symbols, but I don't want to take the time to draw bold letters.
What's that on the bottom?
Squared?
Is it multiplied by V?
Well, you take the length of V times the length of V.
No, on the right side.
Oh, yes, times vector V. Note, this number on top is going to be a scalar, right? That's a dot product are always scalars. The length squared is a scalar. So a scalar divided by scalar is a scalar. And we take a scalar times a vector. So if we wanted to say vector A to be 8, 1, vector B to be, say, 2, 5, projection of A, or of B onto A is equal to. So first, A dot B.
21.
Okay, so 16 plus 5, 21. Divide by
65.
okay, so we did A squared, A first one, the 65. So why is it 65 instead of root 65? Yeah, squares, you want to make sure everybody, because that's the common mistake people make, is they'll put root 65 and forget the squares. And we multiply that times 8, 1. In this case, it's going to give you an ugly answer, but it's fairly simple, straightforward how we did it, right?
So 21 over 65 times 8 and then 29 over 5 times 9.
Yeah.
And then it's
And that would be our vector. So what's 21 over 65 times 8?
2.6.
168
So 2.6, is that exact? Or not exact. So what's
168.
168 over 65 and 21 over 65? Well, look what's here. And so this vector is saying this is how much of B goes in the same direction as A. Any questions? Okay.